Hello, everyone. Thank you for joining today's webinar, Navigating the Retrofit Spectrum, Sustainable Upgrades for Existing Buildings. This is the second webinar in our three-part series, The Transformative Potential of Sustainable Building Retrofits. I'm Allison Posewitz. I'm moderating today's session. We are joined by our presenters, Stéphane Hoffman and Ken Griffin. We are recording today's session and will provide a link to the recording once it is available. We'll allow 10 minutes at the end of the presentation today to answer your questions. Please type your questions into the Q&A feature throughout this meeting. This live session is registered with AIA CES for continuing professional education. If you're an AIA member and included your AIA number on the registration form, you'll receive one AIA LU and a certificate upon completion of this live webinar. If you did not submit your AIA number on this registration form, please email us. The presentation today will touch on 4 learning objectives. Our presenters will explore various retrofit approaches, the appreciation for the heritage and architectural value of a structure, and a strategic evaluation of energy saving opportunities. And with that, I'm going to pass this off to today's presenters.
Hello, my name is Stéphane Hoffman. I'm the discipline lead for building science at Stantec. Our building science teams are kind of often called upon to assist design teams with the design of cladding, glazing, roofing, and waterproofing intervention on historic buildings. Over to you, Ken.
Hi, Ken Griffin. I'm the building analytics service leader for Stantec out of Chicago. I've been working on high performance building analysis for 17 years, working on projects all across the world, from Asia to the Middle East and all over the US. These projects, they range from super talls to data centers. And as of late, I have a big focus, like many on the call probably, on decarbonization through adaptive reuse, repositioning, and retrofits. Okay, so here at Stantec, we place the utmost importance on health and safety. It is one of our core philosophies. Because of this, we like to start out our presentations with a Stantec safety moment. So since the focus of this webinar is retrofitting existing buildings, I wanted to touch on site safety. So on an active job site or a construction site, we want to make sure we are following safety protocols, i.e. wearing personal protective equipment or PPE. So wear your hard hats, steel toe boots, safety glasses, and your high visibility reflective vests. Pretty obvious one, but got to do it. Make sure there is pre-construction safety walkthroughs in place and involve your clients early on to identify potential risks. Meet on site each morning to review site-specific hazards, use signage and visual cues to keep everyone informed of potential safety risks, and provide real-time communication throughout the day, so everyone is up to speed on changes to the work zone. In a nutshell, let's make sure we put policies in place and we follow them so everyone goes home from job sites the same way we got there. Over to you, Stéphane.
Thank you, Ken. So before we start, we wanted to talk briefly about the building's historical context. Ken will have a case study on how building analytics can be used to understand the impact of interventions on existing buildings. It's important that when doing so, we understand the context of the potential heritage value. And essentially, first question is, when is a property more than just an old building? Many of our historic buildings have heritage values, and these can be tied to a number of things, as we'll see in a second. Considering the building's heritage value starts with its age, 40 years is a common threshold. That means that in many cases, we're working on buildings that may have now been built in our lifetime, like this example here of the Michael Graves Portland building that went through a major renovation. We had the opportunity to be the building envelope commissioning consultant for the early stages of this project, in which they completely reclad this building, striving to replicate the design intent of the architect. Many jurisdictions can have an involvement in these. There are federal, provincial, or state level, as well as municipal designation of potential buildings. So it's important that these be explored early in the process so we understand the impact these can have on our retrofits. So what are some of the historic characteristics that give a building heritage value? One that's kind of fairly evident is kind of the architectural merit. There are a lot of examples of preeminent architecture that tie in with either a particular architect or a particular style. This example here on screen is the Supreme Court of Canada, kind of an Art Deco icon from Ernest Cormier, one of the leading practitioners in that style in the Canadian context. It's also an aspect of a potential association either with a historical event or person. This Second Empire House in kind of Ottawa's Glebe neighborhood is known for the fact that it was the home of two of our standing prime minister, and as such is associated with them and some of the events along their prime ministerships. And so for that reason, that building has heritage values. The last aspect in consideration is the community setting. In cases where a building can perhaps not have a particular association with a historic event or person, or kind of be particularly of merit from an architectural perspective, but it reflects the history of the community. In some cases, this may be something that is no longer in the nature of the neighborhood, but it reflects its past. Good example here is the Zibi Block redevelopment in Ottawa. It sits on Chaudière Island in the middle of the Ottawa River. It was a former industrial site. And so this new development incorporated many of the industrial buildings in this development as a nod to the historical industrial past of Ottawa. Once we kind of understand the heritage context of the building, we can then be in a better position to select kind of our approach to the historic buildings. And we'll briefly touch on kind of three different approaches: restoration, rehabilitation, and renovation. Restoration is the highest standard for authenticity in heritage preservation. It is looking to restore the building to a period accurate appearance. And the intent here is to retain as much of the historical fabric as possible, to utilize historic materials and technique in restoring the building, and focuses on compromising sometimes performance in favor of authenticity. That means that it may require more frequent maintenance of certain elements in order to preserve the use of the heritage trades and materials. Alterations should be in keeping with the historic practices of the time. The example here is the center block of Parliament in Ottawa. I had an opportunity to work on this project at the start of my career. We were consulting on the roof replacement and window replacement as part of a major renovation of the exterior of the center block. The windows were replaced with period accurate steel windows, replacing the aluminum inserts that had been installed in the 1960s. But they were done in a kind of interior window and exterior sash, essentially a weather seal, to essentially preserve the historic appearance of the window, use a technology that was kind of common at the time to have a storm window on the outside and a more airtight window on the interior. This allowed us to use the historic steel frames and mitigate the potential for thermal bridging. The roof was also an interesting approach. It had to be insulated so that the attic space could be used in support of expanded office space within the complex. And in order to do an insulated roof, the team went to great details to essentially mirror the exact proportion of all the detailing to accommodate the growing profile of the exterior insulation that was added. A slightly different approach is kind of a rehabilitation, where we're trying to balance maintaining the historical appearance while renewing the functionality of an extending service life for the building. Where feasible, we're looking to retain the historic fabric, But we're balancing the historic materials with more modern techniques as an approach. It's a balance of authenticity and performance as we seek to extend the service life of the building. Alterations should be distinguishable from the historic constructions. In this case here, the Nordstrom building is the former Frederick and Nelson department store built in 2 stages in 1918 and 1951. The historic terracotta was kind of restored, and in doing so, we maintain, the original materials from the second story up by restoring the terracotta in place. We replace some of the narrow pillars that you see at the windows with an architectural cast piece that was lighter and could be individually anchored to address the fact that previous repairs to the terracotta had failed again because of the significant load on these very slender elements in a seismic area here. The ground floor was restored with new terracotta, and the original canopy was replaced, keeping the same kind of profile, but going to a more modern kind of glass canopy. So you can see that kind of balance of the restoration of historic, but also kind of adding some more modern touches. The last aspect is renovation. This is most commonly used when the building doesn't have any specific heritage value, and our goal is most often to repurpose and often improving the performance as well as extending the service life of the building. There are more options available in this category as there's less restraints in terms of accommodating the heritage characteristics. You may retain some of the historic fabric where feasible, but you'll often adapt more modern materials and techniques to the historic structures. You're more likely to have more stringent code requirements in this kind of area where you're especially doing an alternate use for the building. There's an example here from the 1980s is this academic building at Humber College in Toronto. This building was completely renovated at passive house standards to increase its performance and service life for the college. Lastly, as we deal with these heritage buildings and historic buildings overall, there's several considerations that we have to keep in mind. The authorities having jurisdictions have different levels of approvals. As I mentioned at the start, it's not unusual to have different levels of engagement there. Codes and standards have to be reconciled with the historic construction, and the fines that can lead to some compliance issues. So you have to be nimble in kind of addressing how these historic buildings can meet current code or can be accepted from certain requirements. In many cases, you're dealing with obsolete assemblies, and that means that these materials may not be readily available. There may be some challenges in finding some of the qualified trades to do the type of restoration work for a system that is typically not done anymore. So there are a number of these considerations. All of these came into play in our kind of featured case study today, and I'll turn it over to my colleague Ken to walk you through our building analytics was useful to promote the improved performance of this historic building. Over to you, Ken.
Thanks, Stéphane. Right. So what I'm going to be talking about today is an existing building. It is the Mastercard headquarters. It is a really cool project just because as Stéphane had talked about the heritage values, so this one had to be historically preserved. And it led to some challenges, but also led to us come up with some really cool opportunities that weren't just replace glass. It was really interesting. I'll kind of get into all the details. So the project is located in Purchase, New York. It is an office, mostly office, built in 1982. The architect was I.M. Pei. If anyone doesn't know who I.M. Pei is or didn't take a bunch of architectural history courses in school, he is the architect of the glass pyramid at the Louvre. About 466,000 square feet, 4 floors. The big thing is the single plane glazing that has to be historically preserved. And then a pretty standard HVAC system with VAV reheat, natural gas boilers, and chillers. Just kind of wrap your head around where is this located. It is in Purchase, New York. It's about 26 miles northeast of Manhattan, about a 45-minute to hour drive. Purchase, New York is a hamlet or a neighborhood of Harrison, New York, which is a village of Westchester County located near White Plains. So learned a lot about the New York villages this way. A little confusing at first, never heard of a hamlet, but pretty cool. But as you can see on the map, it's kind of where we're located here. It's a little northeast. So how did this kind of come to us? How did this project come to us? So we had worked with Mastercard originally on a project in Dublin, which was a renewable energy study. And after kind of a lot of solid work and a good relationship built there, they came to us and let us know that their headquarters in New York, their bills for their natural gas was about 5 times per square foot of what they were seeing in other buildings. And they wanted to try to figure out what was going on with their current building. So our proposal we put together was for an energy audit for existing systems, MEP, architectural. We're going to look over the utility bills, do a building walkthrough, review MEP operation and the building automation system. We're going to do a thermal imaging study of the envelope because that was one of the first things we thought of. Single pane glass, we're going to have to look at just based on, is there infiltration issues? Is there surface temperature issues? And then we were going to build a calibrated energy model to do some feasibility studies on glazing and on potential savings for replacing the existing system. And the deliverable, we're looking for energy conservation measures, really capital improvement plans. So as I mentioned, how did it start? Started with our audit and our walkthrough. So we got on site and we were looking for existing drawings. We've got original drawings back from 1982, so you kind of see the color there. We're dealing with old drawings here, so we didn't have CAD plans or Revit models. We had this. So we went through all the drawings, took what we could, took pictures, scanned them, got them onto our system. But it was it just kind of showed you kind of what we were starting with. And this is from architectural and MEP. We did our architectural walkthrough on the audit. So what we really did, we were trying to figure out where there are issues with the glass. We were trying to understand temperature, how the spaces felt. The atria was there's 3 atria in this building. There were some temperature issues there that we could feel. The same thing at the existing glass. You could feel air kind of coming around the frame into the building. You could feel the cool air. So we kind of got a sense of the size of the space, but also where issues were possibly coming from kind of firsthand. Our energy audit for MEP system. So yeah, we went through a walk through the whole building. We got a real feel for the chiller plant, the boiler plant, this is a steam boiler plant, the cooling towers. I wrote down all the nameplate data so we can understand what the design performance was of these systems. We put together our mechanical drawings based on our walkthrough and the existing drawings. It really gave us an idea of kind of what we were dealing with in terms of a mechanical system and the distribution as well. The energy out of the BAS system. So we went through and looked at the east and west pavilion and the central pavilion. So that's kind of how it's broken up. And we looked at all the temperature set points. We looked at all the controls. We looked at when systems were coming online, which ones had heating and cooling coils, which ones just had cooling coils, how the staging of the chillers, the staging of the boilers, just trying to understand how the building was operating. What we did learn, though, is what was interesting was that it was kind of manual for the cooling system, where they would look at the weather and they would decide, okay, based on temperature, we'll turn the building on, the chillers on at 4 in the morning to pre-cool the building. Same thing with the heating. So it's a little old school, we'll say. So based on kind of the entire walkthrough, we got an understanding, got an idea of what was happening in the building. We did decide, all right, we do feel like the envelope is our biggest concern here. We still went down the path of evaluating the MEP system, the building automation system. But the real focus we honed in on was the glass, just based on us being able to feel the cool air coming through, the temperature of the glass kind of roasting. So what we did was a thermal imaging survey. And what we did, we took we went there one time, looked at, this was in November 29th at about 7 a.m. with a cloudy condition day, and temperature was about 32 outside. The set point inside, they're looking at 72. And we just did some thermal, the east, west, south elevations. And what we're seeing is temperatures ranging anywhere from we saw a couple of temperatures on the glass at 29 degrees. We had temperatures up in the high 40s, kind of depending on what side you were on. So the east, warmer temperatures, south as well, and the north and west, not quite as warm, but we're still seeing kind of varying temperatures. You kind of see this through the images here, how the different facades played out. You can see the west, cooler temperatures, south as well. So then we went into the inside of the building to figure out, all right, what's our typical indoor conditions? And the existing glass we were seeing about, on average, so we were kind of varying, but our average temperature was about 49 degrees surface temperature for the glass, single pane, and then 59 for the frame, so the mullions. When we started working on this project, Mastercard had already done a double glaze mock-up. So what they had was a double glazed insert added to the existing glass. So the existing glass, single pane, had historic preservation values to it, could not just be thrown out and replaced with a double glazed unit or triple glazed unit. It had to be kept. So they did a study. They did like a live test case of one double glazed insert behind the single pane glass. And then right next to it, they did the same thing with a triple glaze. So you basically had a triple glaze and a quadruple glazed test cases on the building, or in the actual building. So with that, we did some temperature comparisons, and you could see here was a condition on the south, and the temperature ranged in the existing conditions. So before I said 49, 59. Those are just kind of average. For this particular condition, I got to zoom in to see 62 degrees surface temperature. On the new double glaze insert, that went up to 70 degrees. The mullion went from 64 degrees up to 67. And kind of just giving you an idea, this was the existing case we're looking at. Here was the double glazing we were looking at. I'm not sure if you can see my mouse, but with the triple glazing, those temperatures went up to about 74 for the glass and up to 68 for the frame. So you're kind of seeing how this double glazing is improving that surface temperature, which would then improve the internal condition and reduce the need for mechanical heating. So after we did all these evaluations, what we saw was the average glazing surface temperature about 70 degrees with the double glaze insert, 67 for the mullion, and then 73 and 68 for the triple glaze insert. So that's the 4 layers of glass. So you kind of see that huge difference there. And when we're using 5 times the gas that we're supposed to be heating, and now you're seeing this big delta T, you're kind of understanding, okay, this is starting to make sense where the issue really is coming from. So then we went over to, okay, we've identified the issue, we've confirmed it with our thermal imaging survey. Now we're going to our energy model analysis, and we're going to put some numbers behind this. So we use the data from our energy audit. We built an existing building model, and then we analyzed 3 types of glass. So 2 types of double glazing inserts and 1 type of triple glazing insert. We looked at U values, solar heat gain coefficient, and infiltration rate, because we were feeling the issues with the air. I didn't mention this before, but there was also a blower door test done, and we were seeing huge CFM per square foot per Pascal infiltration coming into the building, which made sense based on what we were feeling. And then we were really diving into energy consumption. What are we going to show? Energy consumption, natural gas, and then our peak heating load as well. So I mentioned before there was we said those old drawings. What we were able to do is find a previous project that was a LED lighting replacement, and we were able to talk to the team that worked on that, and they were able to provide us with CAD drawings. Now, for some of, we'll say, people who are newer to the industry, CAD is, at this point, an ancient technology, which was 2D drawing, not Revit 3D. But we were able to give us 2D drawings, and we were able to build a model from that, or energy model from that. Eventually, the mechanical team we were able to build, and our BIM team we were able to build a Revit model for this as well. But basically what you're seeing is kind of a typical office building, large training centers, fitness, collaboration spaces, mechanical down on level 1, interior parking, multi-purpose spaces. Once you get up to level 1 and 2, you're seeing a lot tighter spaces. So a lot more people, a lot more desks, or tightly packed. And then same thing, as I mentioned, on level 2, you kind of see the 3 atria as well, which also was interesting because you're having that heat stratify. So we're having our heating being way high, even though we've got this heat stratifying, which was interesting. And then the top floor, you got other spaces like cafeteria and more amenity spaces. So I said we built an energy model based off of the drawings we had. From there, what we did was we analyzed the glass. So I said we started with our existing conditions. So the glass, the existing performance was, I mean, it was, we'll say the U value was not up to current code. We'll go with that. U value of 1.25. So that is basically no thermal resistance. Solar heat gain coefficient of 0.4. That's because they had applied low E coatings to the existing glass. And the glass is a ribbon glass, so it basically wraps the entire building. The second type of glass we looked at was that double pane insert, and that had a U value of 0.3 for the whole, that had a U value of 0.3 and a solar heat gain coefficient of 0.31. And you kind of see a little mock of how that would look. And the third option was the triple pane insert. So now our U value is down to 0.2 with a solar heat gain of 0.28. So that's super high performance glass. And what we want to do is see, did that reach a kind of a point of diminishing returns with that U value and solar heat gain, but we'll get into that. So we also looked at the infiltration rate as well. So these were our options. We looked at improving the double glaze insert with just the glass and the solar heat gain coefficient improvements. Then we looked at the triple glaze. So option 2 is the triple glaze, double glaze insert, sorry, infiltration rate, no improvement. Second was option 3 was the triple glazing insert, infiltration rate still the same. And then final 2, option 2, then option 3 again. These were the existing double glaze plus triple glaze, talking a lot, and infiltration rate improvements from the improved construction process and fixing the framing system. Whew. Okay, so what did we learn from here? We learned that basically we're getting about 42% reduction in total building energy. So big reduction, mostly from heating reduction with our double glaze insert and the infiltration improvement. And then the heating was the big component. So 63% reduction in heating, 40% reduction in our heating load. So that was the glass that we were going forward with for this project. Now I know they're thinking, people who do energy analysis are like, infiltration rate is kind of a, it's, you can really make a big difference in the building, but that's why we do the blower door test to really understand what it was doing. And then afterwards, another one was done as well to verify. So that was our feasibility study. So as this kind of was coming to fruition, we kind of came to, this is a glass we're going to go forward with. The glass was done by Kilroy Window Systems, and they were doing the installation. But while they were working on that, we reached out to Con Edison to discuss a utility incentive for a building retrofit and for a glazing retrofit, or an envelope retrofit. The incentive rate was about 45 cents per kilowatt hour and $7 per therm. What we'd have to do is we have to submit to Con Edison. They'd have a third-party reviewer. We'd have to calibrate the model to the bills. So we'd done a rough calibration before, but we had to go through a kind of a more stringent process through Con Edison. There'd be a secondary review, a measurement and verification, and then a final review to get the incentive. So as I kind of mentioned, we had to go through a calibration process that was a little more stringent. So we had to be within 5%. So we did some updates to the model based on more current weather data. Before we had used TMY3 data, now we were looking at previous years. And one thing we had to do was, since this was started in 2021, no one was in the building in 2020 or 2021, we had to calibrate to 2019 data. So that was a little different than kind of what we've been used to, because we would average several years out. So instead we had to we've used 2019, and we looked at 2018 as well. So what we're able to do is get to within 1% of calibrating our model for electricity. We also realized was they had about 14% of the total building electricity was offset by their PV generation on site. The gas we were able to get within 3%. That was a little more difficult, but kind of through some calibration process, we were able to get that there too. So what we had was our first calibrated model now calibrated to our existing model calibrated to the utility bills. So we had a good starting point. So everything we had done from there, we can apply to the building for a realistic incentive. So after kind of updating the model for the incentive, going through their process, we broke it down by end use. The building was saving about 62% in total heating energy, going from 1.25 U value down to 0.3. I mean, it made the biggest difference. Space cooling about 20,000 solar heating, mostly. Heat, and that's kind of in line with cooling. Fan reduction and our pumping energy went down as well. So you kind of see the numbers there. Those are a little more micro numbers. Macro, natural gas therms, we reduced about 60%. Electricity, about 17%. That was mostly from cooling and fans. And then our total building energy savings, about 39%. So really good numbers for a retrofit of the glass. Again, we're looking at really old glass versus kind of a much more high performance glass. So this is kind of what we would expect. But when we got down to the incentive numbers, we're looking at about almost about $1.469 million incentive. Now for glazing retrofits with Con Edison, they had a cap of $1 million. So our incentive based on the cost of the actual labor costs and material costs and our fee was a little over $1 million. So the incentive paid off 32% of the total project cost. So that's a good return. So again, we're capped off at $1 million. That's been paid out already. So everyone's happy there. Now, what we did learn though is not everything is, I'm not just going to give you all the good stuff. Some real life things happen. So there were some temperature issues on site. And what we figured out was there were also some cracking happening in some of the glass. So what we realized was there were some issues with thermal, what would we say, thermal stress and some improper installation that caused some issues with condensation in some places and some issues were caused cracking. So those had to be replaced. There were some existing glass on site. So they actually had to remove the existing glass, recreate this off site, and then bring it back to reinstall it. Couldn't just basically add the insert right back in. But we did, there were some things learned. Now, one big thing we learned was the low E coating had not been reapplied. So our solar heat gain coefficient wasn't what it was supposed to be. It was supposed to be like 0.31. It was somewhere closer to like 0.55. So we're getting temperature issues. So the low E coating then had to go on and be reapplied. So real life issues popped up that the model did not account for, but those were corrected kind of on site. But kind of, yeah, it shows you that not everything is just, you model it one way, it's installed, everything's all rosy. Though there are some real life issues that pop up, but we're able to identify them and correct them. So for a retrofit, this was a lot. This is just kind of one of our scopes. And what was great about this is based on kind of how well that went, our client and I have kind of gone back and forth with a host of additional scopes to improve the building in different ways. So we had another scope of work for a chiller replacement, a geothermal feasibility study, a geothermal system design, and along with that commissioning, another incentive program, boiler replacement, a BAS analysis and retro commissioning to help improve the automation and operation of the building automation system. We're working on a skylight replacement now. Now we're also in conversation for additional photovoltaic to the project and possibly some exterior shading on the atria and maybe even separating the atrium so it's conditioned by itself and there's not open to the other spaces to help with some of the temperature issues there. So it's just one retrofit of just the glass has kind of led us to additional work as well. Also other projects with this company too. So it's kind of been a great project just to show how analysis can lead to not just savings. People hear, oh, energy savings. What does that mean? Well, there are incentive dollars. There's costs behind that as well, and there's also benefit too. the next thing I wanted to touch on, so that was kind of the main part in terms of the history and preservation part. What I wanted to the next, which was geothermal system design. I'm not going to get into all the mechanical design part. I kind of leave the mechanical team, or the experts there. But I did do a lot of analysis. My team helped with figuring out what we can do in terms of savings and incentive for the geothermal design as well. So they had, Mastercard New York has additional site around. So you can see kind of to the east here, they've got this land. And what we did is we looked at 160 boreholes for a geothermal system. It's been moved down to about 120 boreholes at the moment. And based on, we had the model, so we were able to use the exact same model. And our original incentive for that geothermal system is looking at a payback, looking at an incentive of $2 million for the geothermal system. And that is based on about $200 per MMBTU for incentive rate. So that's, you know, a nice savings there. Now, while we did this analysis, we were able to provide our geotechnical consultant, PW Grosser. We were able to provide them with the building loads. So they were able to then calculate the ground source temperatures for their design. And basically, they were able to see what load was going into the ground, so they can determine what was going out. And they were able to calculate the temperatures kind of hourly based on our hourly load data. So we gave them cooling and heating load and our outdoor temperature. And then they were able to take that information, run through their calculations, and then provide us back with ground source temperatures for the year, which we were then able to feed back into our model and model that actual ground source temperature. So before we were using about 50, I think it was 55 degrees flat for ground source temperature. Not exactly realistic, but something kind of a starting point for us. After we were able to model the calculated ground source temperature, you kind of see the range there in the winter and the summer. Our incentive went from 2 million up to 2.3 million. So we were a little more accurate with the heat sink and kind of our loads as well. The next part of this was we had a change of our heat pump system. So based on cost of our previous heat pump system and based on kind of some interest in a slightly different system, we looked at Climacool's modular SHC heat pump water-cooled chiller. And what the benefit here really was simultaneous heating and cooling that our previous heat pump didn't have. It allowed us to eliminate valves. It allowed us to, as I said, simultaneously heat and cool. We were able to do, how do we say? We were able to eliminate pumps and replace them with chilled water pumps, and hot water pumps went from 12 down to 3 chilled water pumps, 3 hot water pumps, instead of a singular pump per Climacool system. And it had a higher performance than what we had before. So this new system was kind of an upgrade that kind of happened just based on, you know, as we were kind of getting close to the end of our design, we had our CDs out, and then we kind of found something that was a little better for the project, cheaper and more efficient. It's kind of the dream. So after we incorporated the efficiency of this system into the model, we saw our incentive jump up from 2.3 up to 2.7. So we had started with our geothermal. Actually, let's go back. We started with our envelope, 1.4 million. We got $1 million. Now with our geothermal, we looked at another 2 million. We made it more detailed based on our calculated ground source temperatures, 2.3 million. And now based on our newer Climacool heat pumps, now we're up to an anticipated 2.7 million. We're finalizing this, so we haven't got it finished just yet, but that's the anticipated incentive at the moment. What does that mean? A envelope retrofit project and a geothermal retrofit project. We're looking at about $3.7 million in eligible incentives, not to mention a lot of other work to help improve the building. I mentioned before, you know, energy is great, greenhouse gas emissions reduction is great, but thermal comfort, another big benefit to the people who are actually occupying the building. So, you know, some people, you tell them, energy savings. If you're sitting at your desk and you're hot, you may not care about that. But if we're going to do that for the client and then for the occupants, also make them comfortable, we've kind of, that's a win-win for us. And one additional thing I want to add on here is a quick analysis of future utility rates. So what we're seeing now in retrofits is kind of a urgency to get moving on these projects now. Based on, well, I'll use New York as an example. Washington, D.C. is another big one. In the 2030 estimates for utility rates for electricity, you're looking at about 35.6 cents per kilowatt hour in 2030. In 2021, when we started this, it was about 17.6 cents per kilowatt hour. So we're almost doubling that. So by getting the ground floor here, we were saving about, with our geothermal calculation and envelope calculation, about $500,000 a year in utility rate reduction. That same building in 2030 with the new utility rates, you're looking at about over $1 million in savings. So getting those retrofits in now while the utility rates haven't ballooned up yet is kind of a really good selling point for working on this beyond just kind of the improvement in carbon emissions in your body, carbon and energy savings and your thermal comfort. So again, we have retrofit projects. Look into it now before you're starting, and it's already, you're $1 million over in 2030. A lot of talking for me, but hopefully you guys found it interesting. I love a good case study. Learn a lot. All right, here we go.
Okay, awesome. Thank you, Stéphane, Ken. That was a really an amazing project story. It's really great to see that there's so many opportunities for improving efficiency in existing buildings, and to also see the impactful results that you're able to achieve with that. So we're going to spend the remainder of our time today in a Q&A session. I've seen some really great questions come into the chat. If you have questions, feel free to continue to add them. We do have about 15 minutes that we can answer questions today. So I'm just going to go through questions that they've been coming in. A lot of the Mastercard project. So Ken, this is for you. The first question is, was the Mastercard project a level 2 audit or a level 3 or somewhere in between?
It was technically a level 2 audit. The modeling kind of came on as a addition to that. It wasn't actually an level 3 audit though.
Okay, no. Awesome. The next question, also related to Mastercard. It looked like the triple glaze option yielded slightly lower energy reductions than the double glaze. What are your thoughts on why that might be? Also, was the low E coating used on all facades? Was there any differentiation between a north versus south facade, for example?
It's a good question. So if you look at IECC, they have different solar heat gain coefficients for the north and the east, south, and west facades. I wish we would follow that, but a problem we run into a lot is we want the glass to kind of look the same exterior, interior, everywhere. So this one ended up having the low E coating all around. The previous question, though, ASHRAE level 3 audits, I wanted to mention, we don't see a lot of those, but I think we should. So tell your clients that. What was the first part of that question? The second one?
The first part of the second question.
I remember. I got you. So it was triple glaze versus double glaze. So the triple glaze was what we see with a lot of envelope performance, and let me see here. You have a savings, and your savings is growing, and it reaches kind of a level of diminishing returns. So after 0.3, you start getting, if you jump from, let's say, a 0.4 U value up to a 0.3, you get, let's say, 10% savings. Then you go from 0.3 to 0.2, that kind of drops off to maybe 3, maybe 2, 4. So it kind of reaches a level of diminishing returns. And then based on the cost of that extra, based on the cost of that triple glaze versus the double glaze, it just didn't make sense for the return. We were still getting a great improvement, but yeah, you kind of reach a level of diminishing returns. We see that a lot, even like double pane, triple pane inserts aside. You see that a lot.
Okay, next question. Could you go into more detail on the energy model calibration methodology? What parameters did you change in the model to achieve calibration? And how often did you select those parameters? Also, after the retrofit, was the building energy use monitored and compared to what your model predicted?
Yeah, so for the calibration process, one of the big one was getting the blower door test information for the infiltration rates. Sitting down with the building engineer to get the controls really kind of dialed in. What was tough was, since there's a lot of manual calcs, we had to manually insert a lot of information into the model, which was tough. So we had to set it to be, if the kitchen is below, make it a little more manual. Match these conditions. The other ones were the utility bills. That was a big one. Making sure we had the right schedules, and trying to think of what else we had that was a big deal. Understanding the use of the space, which was really important. I think I mentioned that. Making sure we had the the LED lighting retrofit installed. And then one thing that we had missed out on was a data room, which we were having trouble calibrating. And then we finally got the right load in that room. That kind of got us to where we needed to be on electricity. But again, infiltration rate for models and analysis is tough because it's it really swings from one way to the other, but the blower door test really helped. In terms of the measurement and verification, Con Edison went out and did measurement and verification, and I'd have to get those numbers. I know I have them in an email, but I know it passed. That's how we were able to get the incentive. But yeah, in order to get the incentive dollars, they had to go and have proof of concept. It's a great question. If you reach out to me, I can kind of let you know how that actually played out. But I know it was within 5%. So that's how they were able to approve the incentive dollars. But the thing is, you have to wait a year. So that was kind of tough on the envelope. Geothermal, we're not there yet. We have to finalize that, and then we have to see a year's worth of data first.
Another question related to Mastercard. Are you finding that, oops, sorry, wrong question. Was the existing heating system, or what was the existing heating system and efficiency for Mastercard?
It was a steam boiler. It was kind of end of life. The performance we had calculated was closer to, at that point in life, but closer to 70, I think it was 72% efficiency. So if you're looking at those ground source heat pumps, you're looking at a COP of closer to I think it was 3.5. So a huge swing in efficiency. Now what we did have though was with the geothermal system, we still needed a backup heating plant. So I know there were discussions on not eliminating 2 boilers and maybe just keeping one just for the low amount of hours it got below. I think it was like something like 10 degrees outside. But I think that's still, they looked at electric boilers, the price just didn't make sense. So I think there is still a steam boiler in place for when the ground source system won't be able to meet the outdoor temperature conditions.
Okay.
That was another thing about calibrating it as well, as understanding the current performance. And that was a lot of understanding what it was designed to, a lot of digging through old paperwork, and then just trying to understanding, what it was currently doing. That's tricky, but fun.
Okay, so the next question, for large office buildings in community centers where space limitations make geothermal unfeasible and where aging buildings and window frames prevent triple pane retrofits or full frame replacement, what sustainable retrofit strategies would you recommend to still achieve meaningful energy and emissions reductions?
Well, we can, I'm going to assume low-hanging fruit like lighting retrofits have been done. In a situation like that, for building performance, I would say our best case scenario really is our monitor-based commissioning and retro commissioning. You're looking at the automation system and seeing how it's performing. That for energy reduction. If you want more of a green building, you can look at other strategies. You can look at green walls. That's kind of a different purpose though. I would stick to the MBCX and RCX for spaces where you don't have the opportunity for things like retrofits for HVAC systems or envelope. I think that would be my first recommendation. Bring in someone to look at the building automation system and see where you can make improvements.
Stéphane, did you have anything to add to that one?
Well, the enclosure retrofits are the kind of ones that have the longest impact on the building, but they are kind of more of a disturbance. They are kind of more pricey. You have to work around the existing occupants. But in terms of resilience and redundancy, the enclosure can really pay off.
Okay. So the next question, which I feel like ties into this previous one very well. Are you finding that existing frames are being thermally broken?
That's a great question. We had discussed this before. So what they did here was when they reconstructed it, they inserted polyamide strips into the frames in between the inner and outer frame sections. Now, I don't know if you see that everywhere, but I know they did on this one because making sure it was thermally broken was important to get the performance we wanted. And I didn't mention it before, but the U values I was giving before were the assembly U values or system U values. So that incorporated center of glass, edge of glass, and frame. But yeah, polyamide strips is what they inserted into this one to achieve that thermal break.
Stéphane, any additional thoughts from you?
There are a number of ways of kind of introducing thermal breaks into existing frames. The approach kind of mentioned here is one. The other is to use kind of a cassette style system where you're kind of mounting to the frame for its structural capacity, but providing kind of a whole new kind of veneer system.
Okay, so the next question is taking us back to Mastercard. Why was geothermal chosen as the retrofit option over other options like more solar or heat pumps?
That's a good question. I don't actually recall off the top of my head why we went down the geothermal path, but I know there was a strong push for something a little more progressive, so something a little more something that would use the land they had, and something that was kind of instead of just new chillers, new boilers, or heat pumps, they wanted to do something a little more top of the line. And since they had the land, they thought it was a great opportunity. I think it is too. I mean, I love geothermal systems, and it makes sense when you have the space. Unfortunately, not many have that space. And with the solar, we are looking at more solar now. So that is the next step. So you do geothermal and solar. There we go.
Okay, excellent. So with Mastercard, how would you categorize this as far as what we discussed in the beginning of the presentation today? Would this fall under restoration, rehabilitation, or renovation?
This one wouldn't be one of a rehabilitation. We're trying to kind of respect the historic look of the buildings, but we're willing to use kind of modern technology to enhance its performance.
Okay, excellent. And I believe we have answered all the questions in the chat. I guess we have a few minutes left. Are any last thoughts from you, Ken or Stéphane?
I think we've hopefully kind of demonstrated kind of how the analytics can be used to really kind of assess what kind of type of intervention has the best ability to pay off, how it can be used to kind of balance the mechanical and enclosure elements of a retrofit.
Yeah, and then the one stat I really love for retrofits and even like adaptive reuse is, I think it's on a new construction project, 60% of the embodied carbon comes from the new structure. So when you're able to keep the existing concrete and steel, you're already ahead of the curve. And then you can actually, keep some of that charm of a historic building and kind of add some new to it to kind of bring it up to current code. So it can have kind of the best of both worlds, I think.
Okay, excellent. Well, thank you for that. So just to reiterate, this presentation will be sent out. We'll have a recording available and we will send an email out as a follow-up. So everyone who has registered will have access to that. We have one more webinar in the series. So the next webinar is taking place on October 9th, and our presenters are going to be discussing reducing operational emissions across portfolios and the role of district energy. So by scanning the QR code that's on this page, you'll have access to that landing page with the sign-up form for that last webinar, as well as information on this webinar and the first webinar we had as well. So thank you everyone again for joining us today, and we hope to see you again next time.
Thanks, everyone.